All right, welcome to Walquan Office Hours, week 3, first day Monday. Hope everyone is doing fine. Let's see who's joining us with us today. All right. Hello, I hope you're doing fine. Let's see who else is with us today. I can type here in the chat. Hello, everyone. I see that Rajesh is with us today. Omadara is here. Hello. Hope you are doing fine. Let's see who else is with us for today. The current agendas, we're going to finish up our discussion of heaps. We talked about them. We haven't quite implemented them just yet in Python, so we'll see how we can do that. Zanab is here. Gerald is here. Hello, Gerald. Hello, Zanab. Hello, Ella. Hope everyone is doing fine today. First day of the week, Monday. First office hours. All right. Let me know anything you want to throw on the agenda. All right, someone is asking about the VC mini projects, and we will get to that today. We will, in fact, probably get to the VC mini project. We may not get to exercise 3, 4, and 5, but if you put something on the chat, perhaps I can take a look at that and answer it very specifically. I see that Christian Terina is here. Hello, Christian. It's for Christian. All right. Anything else to throw on the agenda before we begin? Okay, so let's see. I'm going to go ahead, and I think some people are on the wrong link. So hold on. Let's see. Try this link here. I think some people are on the wrong link for some reason. We've had some issues with the links. Subham is here. Hello, Subham. So now Anna is here. Hello, Anna. Let me know any topics to throw on the agenda before we get started. And I understand I started about 5 minutes late for office hour, so I'll go 5 minutes over. I think there is a problem with the link. So there's some issues with the links we're providing, and I think what's happening is I think there's some issue with YouTube and how we're doing the streaming. For that reason, this link may not be the correct one. I think the one that is for office hours is automatically generated. So I think maybe the best thing to do is, if you're following office hours on a regular basis, is to set up notifications when a live stream occurs, because that should give you the correct length always. For some reason, the link we've been using doesn't always work out, so that's what happened this morning, and that's why I went over into that to the other link and said, here, try this. We're still trying to suss out those issues, but to no avail. All right, someone's saying the algorithm mini project, and I'm not quite sure what you mean by the algorithm mini project, but do let me know what you mean by the algorithm mini project. All right, more stuff can go on the agenda, of course. I think we have enough. I'm going to go ahead and do the other link and tell them to try out the link I just put on this chat. so I see Tulu Wasawe, I see Vera, I see Tom. Hello, guys. Welcome to Office Hours. I know some of you guys were on the different link. We're still trying to suss out those issues of why the old link won't work out. So for in the meantime, I will have to have both links to make sure, telling people, hey, try this other link instead. All right, so the VC mini project, that's what you mean. All right, so I put that on the agenda, the VC mini project. Let me know about anything else to throw on the agenda. We can keep on adding to this. And I think what I want to do is let's go and wrap up the IP mini project first. I'm going to wrap that one up and go finish up Heaps and then go into VC. Are the deadlines for the assignments and projects, are there deadlines? And yes. If you look at a lot of these questions, if you go into the important course policies, it's a last day for submit assignments is December 4th, 2020. Everything is due on that day. All right, someone is saying, can we cover Lambda functions, please? Yeah, we can talk about Lambda functions. I can put that on the agenda there, Lambda functions. All right, throw that in there. Get a discussion of Lambda functions, what they are, and good applications for them. All right, so with that said, let's go and take a look at the IP mini project. Let's go and revisit that and finally wrap it up. So let's go into Python mini projects IP. Do kernel and restart and clear that output. All right, do cell and run all above. All right, someone is saying is what they've missed. You haven't missed too much. You just missed me asking for stuff on the agenda and me opening up the IP mini project and wrapping that one up. Let's make sure everything ran above. Of course, there's probably some sort of name error that I have there. So let's go ahead and run this. Now let's tackle this IP, the last question of the IP mini project. So we talked about a better way to find primes. The whole point there is instead of doing this exhaustive search from 2 all the way to the number -1 to check if we have a factor that is easily divisible by, instead we go up to the square root. So our algorithm used to be order n, an order n operation at worst, time complexity order n, and now we have a square root time complexity, square root of n. That was better. However, there's still a better way to look for primes. This is called the sieve, and it's called the sieve of Eratosthenes. I always mispronounce that name. I probably mispronounce it right now. I believe it is someone from ancient Greece, so I'll just call it the sieve. Let's talk about this sieve algorithm and how we can go and implement it for an improved version of finding primes. So we have here in Wikipedia is a GIF of this sieve algorithm. I'm going to refresh so I can follow along with the GIF. So what we do is we take 2 and we start blocking out all the factors of 2. 2, 4, 6, 8, 10, 12, and 14. And the reason why we block those factors of 2 is because, well, they're factors of 2. They're by definition a composite number. They are definition not a prime. 4 is composed of 2 times 2, so it's not a prime. 6 is 2 times 3, so it's not a prime. So we take 2, the first prime number, and we block out all those composite numbers that are created by 2. I hate this GIF because it keeps on running. I wish there was a pause button, so that knocks out all the factors of 2. And what is left is 3, so we go to 3, that's a prime number, and we repeat the process, and we knock out all the factors of 3. And we'll see what is the next number that is left. In that case was, in this case, that should be 5. So 5 is our next prime number. And then with 5, we create all the factors of 5. So 10, 15, 20, 25, all those are composite numbers by definition. So we knock them off. Now what is left? What is the number that is left? 7. Repeat the process again and again. So you can think of it as a sieve. We are knocking out composite numbers. We're creating composite numbers and we're filtering those out. And that's how basically the sieve algorithm works. All right, so someone says the correct way to pronounce it is Eratosthenes. Eratosthenes. Ah, there you go. That sounds about right. Thank you. And then I won't forget the Eratosthenes. I like that. I think that's a good way to remember how to pronounce it. So I appreciate that. I always fumble that name. So sometimes I'll just call it the sieve. All right, someone is asking about filter and reduce. So I can put that there. Filter and reduce. And these kind of go hand in hand with lambda functions. So this might serve a little nice mini lecture on lambda functions. All right, so any questions on how to pronounce? Desmond is your correct name. Sorry, I see Desmond is second, so I thought you were his last name. So thank you for letting me know that Desmond is your first name. Any questions about the sieve algorithm, how it works on a overall level? Not necessarily the details, but how it works on the overall level before we go into programming in Python. Yep, got my bottle of water and tea. All right. I see someone saying a different pronunciation, so I guess I'll have to look that up and figure out the correct way. I wonder if Wikipedia has a pronunciation guide. They might. Sometimes they have a little button you can press to pronounce it. Oh, well, I'll have to check that. All right. Any questions about how this algorithm works on the overall level before we start implementing it into Python? All right. So what we need here are several things. We have them listed. And what we need is a function that will return us a list of true values of length n plus 1, where the first two values are false. So we're going to keep track of what numbers are prime or not prime through this list. So we'll have a list of Boolean values. So if the value of position 5, that will tell us whether 5 is prime or not. I have a list of Boolean values, and we're going to have a function that will construct us this list. And what we'll do is we'll keep on editing this list as we find more and more composite numbers. Then we will define a function called markFalse. It's going to take that Boolean list, it will take a number p, and it will start replacing the factors of p, changing the Boolean value from true to false. And this is applying the sieve. This here takes a value of 2 and says, well, all the factors of 2 are by definition composite numbers, like 4, 6, 8, 10, and so forth. We will mark those, change their Boolean value from true to false. Then we will have the findNext function, which will find the smallest true element in the list greater than some p-value. This here will give us what is the next prime number that we have found, and take that prime number and start knocking it down all its composites. All right, so let's go ahead and try this out. Let's go ahead and program this listTrues function. So we got to return a list of all true values except for the first two. So we could do something like this, false and false plus for I in range of n minus 1, you can say true. We could do something like that. So here I create a list of false and false, and then I create the other elements, and I can use the plus operator on lists to return a new list with all those elements combined. And this should work out the assertion. And that works out. However, there's an alternate way we can write this function. Let's go and discuss an alternate way. And it's through this tertiary operator that we've seen, and I think it's a little hard to read, but let's go and examine this tertiary operator. What we could do is we can say false, and if I is less than 2, else true. So this here is called a tertiary operator because it takes 3 things. And the way to read it, is if this is true, then we use this number or this value. However, else we use this value instead. This is a way we can write a compact if-else statement in Python using this tertiary operator. And the way you read it, because it's not so readable at first, in my opinion, is you check this condition. If this is true, this is what you do. If not, you do this instead. Right, so someone said, don't forget the false false. The false false should be right there. So notice what I did here currently is I create a new list from this first list plus the rest. Because I want to have a list that has n plus 1 elements where the first 2 are false and the rest are true. And that's what I do right here. False false plus the rest. Notice how it's very compact. However, I can use this tertiary operator to do it via one list comprehension. So now what I can do is I can comment this out, and I could say for I in range of n plus 1, and say if I is less than 2, then return false, else return true. Make sure I put the return statement right there. I have a syntax error, so let's examine that. I forgot about the else statement. Right. If I is less than 2, have false. If not, have true. Go for I in range of n plus 1. Let's try that out. Passes the assertions. Any questions about this list true function? All right, so our next function is mark false. So what we're going to do here is we're going to go ahead and take that value p and start marking off all its composite numbers of p in the provided Boolean list. So in other words, for factor in range of 2 times p, we go all the way to the length of our Boolean list of step size of p. Remember, the range function allows us to specify a step size. So in other words, if I have 2, I want to try out 4, 6, 8, 10, and 12, and so forth. So in other words, range of 2 times p all the way to the length of the Boolean list and a step size of 2. So we say for factor in range of 2 times p to the length of Boolean list of step size p, what we're going to do is we're going to take our Boolean list, we will index by the factor, using that index factor, and we will change that Boolean value from false from true to false. And once we're done, we'll return back the Boolean list. Questions about this mark false function. This here is applying the sieve. It's taking that Boolean list, the list we are using, the data structure we're using to store the information, whether a number is prime or not. And we take a prime number, we construct composites of that prime number. So if it's worth 3, we say 6, 9, 12, 15, 18. And start marking all those composite numbers that we form with 3. We set their Boolean value from true to false because we know they are not a prime number. Let's go and assert this, run this mark false function. This works out. So now the next thing we do is we need a function that will tell us what is the next prime number to do. And why are you multiplying p by 2? All right, let me take a look at that right there. We are multiplying p by 2 because that is the first composite number we start off with. So for example, if I am looking at 5, I know 5 is a prime number, and I'm going to start knocking out all the composites of 5. The first one I start off with is 10. So 2 times 5. And the next one I start off with is 15. And the next one is 20 and 25. So in other words, I can write this as, I want to go through all the multiples of 5 basically. And I start off with 2, so I say 2 times p. So I say start off with 2 times 5, and then 3 times 5, and so forth. So that is why I have 2. Other questions people have. Alright, so let's go ahead and flesh out this find next function here. Accepts a Boolean list, accepts p, and we want to find what is the smallest element where there's not a false value. Alright, someone says looping through decorators through hyperparameter search of deep learning models. I'll keep in mind of that. So here, so in other words, what we want to do is if I have the following list here. Oh, we have an example here. True, 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 true. So we want to return a function for the smallest element which in the list which is not false. In other words, true. So in other words, we want to go through this data structure here and find the next true value, which should be here, but under the conditions that we will provide a value p, a start index. So the smallest index of this list here, in which we have a true value, but we want to start off our index at a provided start point. And we're going to use this function here to figure out what is the next false number to use in creating the composites. So what we got to do here is we got to start off with we're looking for the index. We're looking for the index of a data structure. And my question to you is, when we're doing iterations and we're interested in not only the value of a data structure we're iterating through, but also its index, what are the techniques or functions we should use? And while you think about that, let me go and explain this 2 times p. So in this sieve, the way it starts off, we take the value 2 and we knock out 2 times 2, 2 times 3, 2 times 4, and we go forth. And then we say, so notice we try 2 times 2, 2 times 3, and so forth. So we go here into we use a step size of p. So in other words, if we have a value like 5, we will start off with 2 times 5, and then we do a step size of 5, so that means we have 3 times 5, and so forth. So yes, you can think of this number here as increasing. 2, 3, 4, and 5, because we are using a step size of p. Remember, if we go here, just a little play around with range, we can say for x in range of 2 times 5, and we say let's go all the way to 25 of step size of 5. Print out x, 10, 15, 20. All right, so I see enumerate. That is correct, guys. We have to use enumerate. Let me know if that explains why, further why this 2 times p. Yeah, so we have to use enumerate. So we say index val in enumerate p, Boolean list. However, I don't want to go through the entire Boolean list. I want to find the smallest element which is not false and is greater than p. So I can index into the list. I can say, let's not iterate through the entire Boolean list. We have to start off with that p plus 1 and go all the way to the end. We're not looking for what is the index, the smallest index with a true value. Looking for the index that has the smallest index with a true value at a given start point. So now I can say index val and enumerate, so iterate through the index and the value. And if I can say, well, if val is true, and here I'm using, given the fact that these values are Boolean, so if val, if it's true, then what I need to do is I need to return the index. Now, I forgot the for loop right here. For index and val. And if I don't find anything, then I will return none instead. Let's run that function there. Let's go ahead and check the asserts. I get a name error. And oftentimes, most of the times you get name errors is because you probably have a typo. And that's probably what I have there. I had a typo right there. Let me fix that. Let's try that out. And I still get a name error because I cannot spell this morning. And enumerate. Probably a dead giveaway there is that since this is a built-in Python function, it should have a special highlighting. I didn't have that before, so there you go. Run that. And I still get an assertion error, so I must have a mistake. So let me see if I can examine what is going on in my function. Or if you know what's going on, let me know. I think I know my source of error. I know my source of error. Anyone want to point out what I'm doing wrong here? All right, so I see an alternate solution. Let's try that out. Let's go ahead and try that out. So what you did there is you said for I x in enumerate of our Boolean list, and if I is less than p and x equals true, return I. Let's try that out. I'm going to go ahead and wrap this around a different find next Boolean list, and p and that gets an assertion error. So maybe let's see if I, oops, wrong one. Wait, no, that's right. For Boolean list, I and p, and return I. That still gets an assertion error. So I may have copied your solution wrong. Return I. So one thing I want to point out is that in Python, you can just avoid saying x equal true. Since x is a Boolean value, you can simply have and x. However, let's go ahead and, so Kinja, let me know if I copied something wrong in your function, but something is going wrong. You want to be able to point out what is going, oh, that it is, that's what it is. Find, sorry, thank you. Different name. Yeah, so Kinja, your solution works out. All right, your solution works out. I had a typo, lots of typos this morning. So I made the fix here where I set, let me go ahead and emphasize this once again, is that since x is a Boolean value, since it's true and false, we should just simply say, we can, this is right here is redundant. X equals true, we can just say x. All right, so that works out. So thank you. And so we're making sure that I is greater than p. However, in my solution here, let's see if we can fix this. Let's see if we can fix this solution here. So one thing to keep in mind is while we iterate through, let's go ahead and try this out. Let's say my list is equal to 0, 1, 2, 3, 4, and 5, and 6. And if I say for I, val, and enumerate my list, but I said let's start off with position 2, and I print out I and val, what do we notice? Let's figure out what is wrong with the solution I propose, and let's fix it. So I index and say, hey, let's not start off with our current, the 0 position. Let's start off with this position, p plus 1. I tested it out here, but what do I see is wrong? Yeah, so I fixed that. I renamed it to find next. So that's why your solution works out, Kinja. So sorry about that. But why is the solution that I wrote out wrong? There's something wrong about it. And I thought I was being clever. Because I said, you know what? Let's start the enumeration. Let's start our list not at position 0, but let's go and start off at p plus 1. Right? Since we're looking for the first true value with a value greater than p, well, let's start off with p plus 1. And right, and if val is true, return the index, and if we don't find it, return none. So why didn't it work out? I thought I was being clever. And I tried it out here. And what is going on? So notice what's going on here is that if I index this list, so I say start off with 2 and go all the way to the very end, and I print out the indices, I start off with 0. So the index of 2, it's not 0 in the original list. It should be 2. So what I need to do instead here is the enumerate function. If I look at the documentation of the enumerate function, there is a start index. So by default, it's 0. So in other words, if I use enumerate, I can start off with any starting index. I can say start off with 2. And that works out. I can do anything. I can say start with 10. So I can specify an optional start index. And that's what I need to do right here. So let me fix that and say, you know what? Let's start off with p plus 1. Run the find next function. Run the assertions. And that worked out. All right, so 2 different solutions. Same thing. Same result. Questions about what I did? So let's go ahead and flesh out this prime from list. So given a list of true and false, return the index of the true values. So we only want to return the indices of the true values of that Boolean list. So that shouldn't be too difficult. Right, we can iterate through. We can say for I in range of length of our Boolean list. And if the bool list of I is true, well then we want to keep that index. We can probably go ahead and do enumerate, right? For enumerate, say Boolean list for I val, right? If val, let's keep that index. That should work out. And now we have a function called sieve. We got all the pieces together, so let's go ahead and try that out. All right, so that works out. Let's time our solution. Let's use the sieve and let's use the get prime to see how much performance gain, how much faster it is. Let me know if people have any follow-up questions regarding the sieve question. But one of the things that we saw here is that oftentimes your solution to some problem, you could write it all down in one function. You can have one grand function that does your task. But this function can be very long. So a better approach is to break this function into multiple functions. And then have a main function here that's going to call upon these pieces. So don't feel like you got to force everything into one great big function. Break it down. Compartmentalize it. Separation of concerns. And that's what we did for this mini project. All right, so it looks like it took about 1 microsecond, a little less than 1 microsecond using the sieve, and it took about 5 microseconds using the old method. All right, so any follow-up questions we'll have before we move on? I can scratch that from our list, from our agenda. I think I want to talk about these filter and reduces in Lambda functions. I think that's a great segue here. So I'll have to punt VC into tomorrow, no problem. And we can continue our discussion of heaps later. And there was also a discussion about hyperparameters and convolutional neural networks. And the short answer, well, since this is class, it's more focused on the core fundamentals of data science and not necessarily a machine learning. I won't go into all in depth of it. But with neural networks, hyperparameter tuning is a lot more complicated. So if you're going to do that, you might want to suggest an alternate way as opposed to maybe a brute force approach, like a grid search. So I would suggest that you look into Bayes search cross-validation as an alternative to traditional hyperparameter tuning techniques. And you could write a decorator that you decorate your function and it will do the hyperparameter tuning for you. However, what I really suggest you do is look into Bayes search CV. If you're in the realm of Python, this is found in a package called scikit-optimize. All right. Let's go into office hours, open up a new notebook, and let's talk about these Lambda functions and maybe how we can use them with filter and reduce. All right. So in Python, we saw how we can create a named function. So we say def my function accepts a and b, and return a plus b. And that was it. Right, pretty simple. We define a named function, and then we can go and invoke that named function. And the reason why it's called a named function, well, is because it has a name. It's called myfunc. This function has a name. So we're saying named functions, so if we have named functions, do we have functions that don't have names? And the answer is yes. In Python, we have functions that don't have names. All right, we talk about named functions, so why we put an emphasis? Why did I say named functions? Because in Python, we can have functions that don't have names. And if you don't have a name, or if something doesn't have a name, it remains anonymous. If we don't know the name of some person or something or some entity, it's anonymous. So in Python, we can have functions that have names like we have here, but we can also have functions that don't have names. They remain anonymous. And in Python, they allow you to write what are called lambda functions or anonymous functions. These are functions that don't have a formal name to them. So let's go ahead and try something out. Let's say we want to go ahead and let's see. Let me think of a good test case. Let's try reduce. From functools, import reduce. And we have a data structure 0, 0, 1, 2, 3, 4, and 5, and 6, and we call this my list. And what I want to do is I want to multiply I want to add up all the numbers in the list. So I could use sum in my list. I can do that, sum my list, and get the answer. Or I can use this reduce function. And the way that this reduce function works, it says give me a function, and I will use that function throughout the data structure. Actually, I'm going to back up and not use reduce, but use map. So map is a Python function. We'll talk about reduce later. I first introduce map. And then, so map is a Python function that says, hey, give me a function and give me a data structure. And I will take that function and use it in all the elements of my data structure. We will see map operations when we go into pandas. Pandas have its own mapping type operations. But what it's saying here is give me a function, and I will use that function throughout my data structure. So for example, I can say, maybe I want to square all the elements of this data structure. So what I can do is I can define a function called square that accepts the value x and returns x squared. So I pass the function and I pass my data structure. I can say for x in map, print out x. And notice what it does, I can iterate through and print out the values. So map returns an iterable. So I can say for x in map of square in my list, print out x. And I print out the square of all the numbers in my original data structure. So notice it takes two things. It takes a function and it takes a data structure. And this function here, notice we're not calling that function. In other words, when you don't have something like this, we don't have these open and closed parentheses. We're not making use of the function immediately. What we are doing is we're just handing off that function to the map function. Saying, here's the tool, here's the function, here's the data structure, use it. Do whatever you want to do. Questions about what we've done so far? Now the problem with this is that this would have required that I had some forethought before I used map. Do we not use map with zip2? Yes, you can use map with zip2. Yes. So the problem with this is that it requires some forethought. It requires that I had to formally create this named function before I used it. So it would be nice if when I use map, I can create that function right there and then. The other problem here is that maybe this function, maybe I'm only going to use it once, only in one place. And that place can be right there in the map. So my code has a function called square that I only really use in one place. So my code base is taking up value real estate, right? It'd be very nice if I'm only use this function, that I just define it only at the place of usage. Someone is asking about map, and map can take any data structure, anything that's an iterable, anything that can iterate through, it should work out. So anything can iterate through, map can take. Doesn't have to be a list. In fact, it can be outputs of other map operations because map returns an iterable. So I got two problems I want to solve. I have to have the forethought to define this named function before I use it. It'd be very nice if I can define it, create it at the point of usage. And the other problem is that, well, if I'm only going to use it once, it's distracting because I have other functions that's just going to, make my code go bigger, and I see this function and I only really use it one place. It'd be very nice I can just have a way in Python, some sort of mechanism to define a function for a one-time use at the point of usage. Someone saying, is map a transformation or an action? And you might be referring to Spark. And if you're referring to in the realm of Spark, then we're not there. This is a very generic map operation in Python. But in Spark, map will be a transformation, if that's what you're trying to get at. So Python has a way for us to create anonymous functions. So let's try that out. For x in map, and what I'm going to do here is I'm going to say lambda x colon. This here is how we create an anonymous or lambda function. So we say lambda x. You can think of that as defining a function that has no name, that has one argument x. And what follows the colon is what is returned by that function. So we say return x squared. So that's the first argument to map. Before we gave it a function square, but here we say lambda x colon x star star 2. In other words, we're going to define an anonymous function that accepts one argument x. And what does it return? X squared. The second argument is our data structure, my list. And I can say, I think I'm missing a parentheses. No, am I missing parentheses? For x in map of square. I think I'm fine. Print x. And I get the same result. So notice here, the function I passed to map was defined at the point of usage. And this is great because this function here, I only want to use it on this one place. I didn't have to create a very formal named function right up above. And we will talk about pandas. Someone is asking best use a map in pandas. In pandas, they provide its own map utility called apply, and we will see that when we get to that point in the class. So we will talk about that. We'll talk more extensively about office hours, those operations in pandas. So we will get to that. All right, questions about this anonymous function that I used here. So I'm unaware what a VLOOKUP or a match is in Excel, so I cannot answer that. But when we get to pandas, we'll talk about pandas operations, and you can start seeing what those pandas operations are, what the equivalent are. They are in Excel. So questions about what I have here for these anonymous and lambda functions. They're a great way to create a one-time use function to be used at that point. Notice they don't have a name, hence anonymous. Does lambda need to be in a map? The answer is no. These lambda anonymous functions can be used for other functions as well. For example, they can be used in the sorted function. Can lambda be made for more complicated functions of just one-liners? And the answer is no. For better or for worse, Python has restricted the uses of anonymous Lambda functions. If you cannot express it in a single line, then you cannot use anonymous function. And the point there is, if you want to define an anonymous function that is rather complicated, can be more than one line, then maybe it's not a good use for anonymous function. Right? If I'm trying to have multi-line, it's not going to lead to a very readable solution. Your code won't be as readable if you're using a very complicated Lambda function. So Python said, well, we'll just restrict the creation of lambdas as a single line. And someone says, can Lambda have conditionals? And the answer is yes, Lambda can have conditionals, as long as you can express it as a single line. And that's where the tertiary operator comes into play. Remember, we saw that tertiary operator earlier? We said true. I think we said false if I is less than 2, else true. Remember, we had that tertiary operator? It doesn't know what I is, of course. Set I to 5. We can use that tertiary operator in our anonymous function. So let's try that out. Let's see if we can write an anonymous function that will use this map operation. We'll use this map function to iterate through my list. But if a number is less than 3, we keep it as is. But if it's greater than 3, we will square it. Let's try to do that using an anonymous function. If a number is less than 3, we leave it as is, but if it's greater than 3, we will square it. And we'll see how we can use conditions in Lambda function. So if I say map lambda x, I say x, if x is less than 3. So if x is less than 3, we leave it as is, else we square it. And we give it the iterable mylist. Let's iterate through for x. And that result, let's print out x. We see 0, 1, and 2 are left as is, but everything else is squared. So notice we were able to have a condition in our Lambda function using this tertiary operator. Now, if you wanted your output of map to be a list, well, you can pass it to the list constructor. So this here returns an iterable. You can pass into the list constructor, and now you have a list version of your results. So here we saw the use of anonymous functions and this map operation. Someone's saying, would apply lambda x colon x star star 2 give you a similar output? And the apply method is for a pandas data structure. So yes, if you have a pandas data frame, you want to square all the elements, then using apply lambda x star star 2 would give you the same answer. But the apply method is for a pandas data frame, so we must have a pandas data frame. There's more to talk about with anonymous functions, and when we get to reduce and filter, because I still want to talk about that, it made more sense to first introduce anonymous functions before we get to filter and reduce. And we didn't quite get to VC, but we definitely will get that tomorrow. I know some people have questions on that, but we will get to it. Any quick questions people have regarding anonymous functions at this point? Or map? If not, take care, guys, and we'll see you tomorrow.